Hello, everybody. Welcome back. Today we will be talking about kind of like a subsection of section 3.1, and this is basically after the talk that we have about the power rule, something that I kind of need to sneak in there because I didn't realize that this was actually going to happen until the very last minute. But anyhow, the two questions that we're going to be trying to answer today is there a polynomial that is its own derivative? And also, what is the derivative of e to the x? So both these are going to be essential for the next part. So that's why I need to kind of sneak those in. So the first question right here, let's go ahead and see if we can answer that one together. Is there a polynomial that is its own derivative? And I wrote down underneath it the power rule that we learned from this section, where if we have, say, a polynomial where the function is y is equal to x to the n, where n is does not equal to 0, then the derivative is going to be n times x to the n minus 1. Basically, the polynomial will lose or diminish one of its exponents, and then that's going to be the derivative then as a result. So, right off the bat, we think to ourselves, okay, well, the answer is most likely going to be no, because every time we have a polynomial, if the derivative is one less degree, then how can its derivative be itself? Well, what if we had a situation where the polynomial went on forever? So we have to kind of like think outside of the box for this one then. So here, let's go ahead and get started just to give you an idea, right? So I'm looking for the following. I want to know, is there a p of x, right, where p of x is a polynomial, where if y is equal to that polynomial, then y prime is then also equal to that polynomial then. So I want to know if there is a polynomial such that this is going to be true, okay? So here, let's get a starting point. Well, one answer you might think of is basically 0, right? Because if I say y is equal to 0, then y prime is also equal to 0. Well, that's not really interesting, unfortunately, because that's the trivial answer, and I want to go ahead and go beyond that. This is what is known as the trivial solution, so it's not very interesting, but it's still there nonetheless. Here, how about this one? Well, what if I had y is equal to 0 plus 1, then its derivative is then equal to 0. So note that how for these two equations, they both have different setup. One is y is equal to 0, the other one is y is equal to 0 plus 1, which is technically 1, but they both have the same derivative. And that does happen, right? Because if you have, there are infinite number of polynomials where they all have the same derivative then. So, for example, if I say x squared plus 5 is equal to y, then y prime is equal to 2x. If I have y is equal to x squared minus 3, you can see y prime is going to also equal to 2 times x. So because they all differ by some sort of vertical shift, then that means that they have the same derivative. And that makes sense because remember, the derivative talks about the slope of the graph, which should be consistent because if you're shifting the graph up and down, your shape of the graph should not change. So now what I want to do is I want to build off of this. Well, you can kind of think of this as a, relationship between, like, say, a teacher and a student then. The teacher is going to be kind of like the original function, and the derivative would then be the student. And what is happening is that the student wants to be like the teacher in the sense that, they want to have the same equation. So here's what I'm basically saying. Well, if that's the case, then let's look at this scenario over here, right? Let's say that y, now the students say, okay, well, I want to make sure that I'm the same as the teacher. So that means that my equation should be 0 plus 1. Then that means then the teacher would then say, okay, well, then my original equation should be 1. And then plus, now what is the function that has a derivative of 1? Well, one would then say it's going to be x, right? So you can see how this kind of works out then in this case. So you can see that you have the 0 plus 1 as my derivative, and then you have the 0 plus 1 characteristics in the original equation, but then there's an extra x that's added on. Well, going back to what we're saying, hey, you know what? Now the student said, okay, I want to be just like the teacher, so that means I'm going to go ahead and say that my equation is 0 plus 1 plus x then. And then the teacher would then say, okay, then that means that my original function is going to be 0 plus 1 plus x just to match you up, right? Because you can see how it's still the same function. But now the teacher says, okay, well, I want to make sure that I would get the derivative that would give you x over here as a result. And in order to do that, then that means I need to add on the x squared divided by 2, because that derivative is going to give you what you want. And still, the student is not satisfied. It's like, hey, you know what? If you add on that part, I got to add on that part too. So now the student says, okay, well, I'm going to go ahead and copy you, teacher. So 0 plus 1 plus x squared over 2. And I want that to be my original function. And the teachers then said, okay, so if you have that 0 plus 1 plus x squared over 2, just matching what you want because you want to be like me. Now the teacher has to say, okay, well, what do I have to add on to compensate for the x squared divided by 2 that would be in the derivative? Meaning, what function, when I take derivative, will give me x squared over 2? Well, then the teacher says the next part is going to be x to the third divided by 6, okay? Because you can see by the power rule, that's what's going to give you x squared over 2. Repeating it one more time because, after a while you get tired of seeing the same thing. But nonetheless, what's happening is now the student says, okay, well, I am going to go ahead and take that, and I want that to be my function then. So 0 plus 1 plus x squared over 2 plus the new x squared, x cubed over 6 that you added on. So I want to be the teacher once again. So then the teacher says, okay, fine. If you're going to be like me, then I got to match up with you, right? Just to make sure everything makes sense. So it's 0 plus 1 plus x squared over 2 plus x cubed over 6 plus, note how every single time what's happening is that the teacher, when they take the derivative, it matches up term for term, right, what the student actually has. So now the question is, well, what does the teacher have to add on to the next part in order to compensate to get to that x cubed over 6 then as a derivative? And that's going to be then x to the fourth divided by, 24. Now, this basically goes on and on and on and on and on and on and forever. So if that is actually happening, where you're kind of like going back and forth between y and y prime, right? Saying that, hey, if y prime wants to be the same thing as y, I need to kind of like, add on one more term to my polynomial. We could potentially get our own derivative. In the end, basically, this is what I'm seeing is happening. If my function y is equal to 0 plus 1 plus x squared over 2 plus x cubed over, according to what we have on top, 6. And I'm not going to write 6. I think I'm going to write it in a term that makes me make a little bit more sense to you. How about 3 factorial, right? And then plus x to the fourth divided by, instead of 24, I'll write that as 24 factorial. Oh, sorry, not 24 factorial. Is going to be x to the fourth divided by 4 factorial, x to the fifth divided by 5 factorial, and so on and so on and so on. If this right here is our polynomial, and this goes on forever, meaning it does not end, then that would potentially work. Because, let's check it just to make sure it does. Here, if I take the y prime of this guy, let's see. The derivative of 0 is equal to 0. The derivative of 1 is going to be 0. The derivative of x is going to be 1. The derivative of x squared divided by 2 is going to be x. The derivative of x cubed divided by 3 factorial will be x squared divided by 2. And then we have x to the third divided by 3 factorial. And then x to the fourth divided by 4 factorial, and so on and so on and so on. So yeah, even though the degree is diminishing according to the power rule, since this goes on forever, then we actually don't care because, there are infinite number of terms for us to diminish and to compensate for. So this right here, that is going to be our special polynomial that will allow us to actually have our own derivative. In a notation that might look a little bit familiar to you, y is equal to the summation starting at k is equal to 0, or n is equal to 0 in this case, actually, because that's my starting point. Let me go ahead and change that up a little bit. So here, n is equal to 0, and it's going to be reaching towards k. And we have the function, looks like it's going to be x to the n divided by n factorial. And the entire time, what I'm going to do is, and this is part that's a little bit sneaky, right? And, just relating to what we did in chapter 2, y is equal to limit as k approaches towards infinity. So this guy right here, that's going to be the same thing as this guy over here, and that's going to be our polynomial. Now, in terms of why is this useful, or what is the whole point of this? Well, let's just go ahead and take a look as to what this graph looks like, and then that might give you a better idea. So we're going to go over here to Desmos, and you can see that I have that equation up there, right? And I can set the parameter of k, so then that way you can see what happens as k increases. So if k is equal to 2, then that means you have this. K is equal to 3, you have this polynomial. K is equal to 4, you have this polynomial. K is equal to 5, you have this polynomial, and so on and so on. So you can see the polynomial is getting bigger and bigger. But now let's go ahead and go to like some pretty big value. Let's say k is equal to 20. So now you can see that it's actually changing shape, and it's not something that we're familiar with. Keep in mind, k is supposedly going to approach towards infinity. So we're going to go ahead and go up a little bit more. So let's say 21, and then 22, and then 23. So notice what's happening. It's kind of like flattening out, right? And as k is going to reach, let's say now 30, right? And now you can kind of see a better curve as to what that polynomial actually looks like, because it's kind of like defining itself on the left-hand side. And let's see, let's go ahead and go up to maybe like say 36 and then 37. And by then you can probably see that it's going to stabilize and as a result. So this right here is the shape of our polynomial, where its derivative is always going to be itself then. Now this hopefully looks somewhat familiar to you because it looks like an exponential function. So we're going to go ahead and keep that in mind, and we'll come back to that in just a little bit, okay? All right. Now, back to this guy over here. Our second question, what is the derivative of e to the x? Well, the derivative of e to the x, I think we're going to have to use the formal definition of derivative here then. So let's say that y, or f of x, is equal to e to the x. And what I want to do is I want to find out what is f prime of x using the formal definition of derivative. Limit as h approaches towards 0 of e to the x plus h minus e to the x all divided by h. Clean this up a little bit. Limit as h approaches towards 0. The e to the x on top, I can go ahead and factor out, because we have e to the x times e to the h minus e to the x all over h. Okay. Let's see. Limit as h approaches towards 0. The e to the x, they all have in common, so let's go ahead and take that out as we said. And this part right here, now hopefully you can make this leap of faith. The e to the x, I'm claiming that I can actually just take it out of the equation, because look, the variable over here is plano x, so that has nothing to do with h. So that's why I can just go ahead and take it out of the limit, because the limit deals with h specifically. So it's just a plano multiplier. So now if we could figure out what this guy over here is equal to, then we're pretty much done. Unfortunately, we cannot do this by hand, so I'm going to go ahead and use a calculator to help me out a little bit so you can see what's happening then. So we're going to go to the calculator over here, and you can see that I did set that up, e to the x minus 1 all over x. X is basically h in this case because there's no h in this graphing calculator. And I want to find a limit as it gets closer and closer to 0, right? Because that's where h is approaching towards. So here is the graph of it. And let's see if we can kind of trace this. So let's see, 0.1 is equal to x. So right there, and I'm going to go ahead and close in a little bit more. And now let's see, 0.01. And then we have 0.001, and it does look like it's approaching towards something, and that something is supposed to be 1 then. And let's just make sure from the left-hand side the same thing. So 0.9, sorry, not 0.9, negative 0.1, right? And then we have negative 0.01, and then we have negative 0.001. And you can see that, yeah, from the left-hand side it's also approaching towards 1 then. So one would say that the conclusion is that this guy right here is going to be equal to e to the x times 1, and lo and behold, look at that, the derivative of e to the x is just itself. So that's going to be y prime. Well, in that case, then let's go ahead and put the two together and come up with the magic then. If the derivative of e to the x is itself, and this polynomial that we found that is itself, then one might say that by the transitive property, those two are exactly the same thing. So that is to say, e to the x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the fifth over 5 factorial, and so on and so on and so on. Or if you want, you can write it as limit as n approaches towards infinity of the summation starting from n is equal to 0 to k, and actually that should be limit as k approaches towards infinity. So let me go ahead and change that. Of x to the n divided by n factorial. And let's just verify one more time, going back to decimals, just to see this. Right here, right? Remember how we had that curve, which is supposedly its own derivative? If I go ahead and put in y, whoops, not y again, y is equal to e raised to the power of x, then you can hopefully see that the two graphs, yeah, they overlap each other, so that means that they are definitely the same thing. So there you go. Then that means that e to the x, what's nice is it's an exponential function, but what we did was we wrote it out as a polynomial because, hey, we just could. And if you're wondering, okay, well, what's the point of that? Later on, when you find out that if you have an equation and you can write it out as a polynomial, it'll make your life that much easier in calculus. And in fact, here, if I take this guy and I substitute x is equal to 1, you can probably use it to estimate what e is approximately going to be equal to then. So that's kind of a cute thing that you can try. All right, and there you go.